So let's consider a game with I players. Each player can play a strategy SI. So SI is the strategy actually played by player I, and it's an element of the set of strategies available to player I. We can then look at all the strategies played by the I players, all the players in the game, to define what's called a profile of pure strategies, which is a set of strategies actually played by each player. This profile of pure strategies is really a subset of the Cartesian product of all the sets of strategies available to each player. Okay. Now suppose that each player has M pure strategies in the set SI. So the set of strategies available to player I there are M strategies in it. We use the subscript I to designate that it's player I, and strategies go from 1 to M. Now we can then assign to each such strategy in the set the probability that it's played by player I. So we can define a simplex here, which is simply really a list of probabilities associated with each strategy in the set. That are available to player I. Okay, so this is an element of Rm. Now, of course, because these are probabilities, every element here is non-negative and for all m and must add up to 1. All right, so if I add up these probabilities, of course, they add up to 1. Okay, and I guess I should here define this like this. This simplex has a name. It's actually called the mixed extension of capital SI. A pure strategies can simply be viewed as a special case of a mixed strategy where the probability distribution is degenerate. So if any of these has actually a probability 1 of being played, and all the other strategies have a probability of 0, then the probability distribution is degenerate, and we have a pure strategy here. So another way to think about it is simply to say that given player I's pure strategy set SI, a mixed strategy for player I is simply a rule to assign to each pure strategy in the set, right, a probability that it gets played, and the probability is denoted as follows for player I. So we put subscript I here. This is the probability that the pure strategy is played. It's and the sum, of course, of all such probabilities for all strategies in the strategy set is equal to 1. Now, a profile of pure strategies is simply the list of strategies played by I players. A profile of mixed strategies would simply be the profile of probabilities that each such pure strategy be played. And of course, these don't need to add up to 1 because these are strategies being played by different players. What needs to add up to 1 instead are the probabilities assigned to strategies within each player's strategy set as being described here. Yeah. Now, if the whenever we look at a profile of pure strategies, we know what the payoffs are for all the players, and let's say that player I's payoff, given this particular profile of pure strategies, is U sub I of S. We can define the expected value of the payoff for player I for the profile of mixed strategies. We just need to multiply all these probabilities together because we need to figure out the probability of the payoff arising, and that's simply computed as the probability that all pure strategies get played. So we multiply these together. This is some kind of expected value. Now, if we do this for all possible mixed strategy profiles, okay, so we have multiplied together probabilities that pure strategies get played, and that probability is in turn applied to the utility of the payoff for player I for the payoff given the pure strategy profile. But if we do this for all possible combinations of strategies being played by all the players, here I'm being kind of loose with my notation, but this capital S here is a Cartesian product, right? We're looking at, all possible combination of strategies being played by all the players. Then if we do this for all such possible combinations of strategies being played, and we add it up, we get a von Neumann-Morgenstern utility from the mixed strategy profile. So we get some V and M utility.